Further maths day 2, equations of planes. Right, so what I'd like you to do is think about having a plane in front of you. So a simple plane, like this piece of paper or this screen right here. And any point on that plane, so if that red dot is a point on the plane, we can call that A. So there's my plane, there's the point A. And to get to that point A, I can go from the origin and I could use the vector A to get to that known point. Okay, so if the known point had the coordinates 1, 3, 6, the vector A would be 1, 3, 6, drawn as a column vector. Okay, right. All the other points on that plane, so every single other possible point, okay, and this is an infinite plane, so it goes off in all directions, but every single other point on that plane we have a position vector r. So from O to another point on that plane would have r. It could be anything. Whereas, as you remember from previous lessons, the r is the general point x, y, z. So there we go. There's an example. That's just one example. It could have been absolutely anywhere we like. Right. So the line connecting this general point to the point A, if I wanted to work out that vector just there, we could call it r minus a. Why is that? Because if I wanted to get from A to that, I would have to go back down A, so that's a minus A, plus the vector R. And again, it doesn't matter where the point was, as long as it's not A itself, whatever point we like, that would have the vector R minus A to get to any generic point. Right, so the normal. So we just did loads of work on the normal vector. You know what the normal vector is. The normal to the plane is something that is perpendicular to that plane. It doesn't matter whether I drew it there, I could draw that perpendicular on this side. It's perpendicular, it sticks straight up. The best way of thinking about it is if you imagine you've got this piece of paper or this screen in front of you, a line coming straight out from that screen, straight to you, would be perpendicular to that screen. If it shot off at a different angle, it wouldn't be perpendicular. Okay, so I know, because it's perpendicular, that if I found the dot product, the scalar product between those two, it would have to equal naught. And we know that because the scalar product of any two perpendicular lines is always equal to 0. Because the fact it's got the cos function in there, cos 90 equals naught. So that's a fact I know. What I'm going to do now is expand those two brackets out. Well, that bracket out, remembering keeping the order correct, so r dot n minus a dot n has to keep that order the same, although in this case, the scalar products, it doesn't actually make any difference, okay, because you are multiplying those together, but it's good practice to write it the same way. Then what we get is r dot n equals a dot n, or the scalar product of r and n is equal to the scalar product of a and n, okay. Now just looking at that on here, that's what we figured out so far. So we've got the normal vector just there, r dot minus a, and we're looking at the scalar product between each of those, and it's going to be absolutely identical is what it says. Okay, so we've just seen that. We've just proved that, or showing that that fact is always true, okay, for any generic plane. Now then, what's worth noting in your notebooks is that a is a vector to a known point on the plane. So exactly the same as when we did equations of lines, the a vector was always a known point on the line. It stands true for planes as well, that the A is a vector, a known point that actually lies on the plane. The n value is a normal vector to the plane. It's got to be a perpendicular vector to that plane. And you'll get used to hearing those same words, normal to the plane. It means it's a line that is perpendicular, cuts through at exactly 90 degrees. Because both A and n are constants, okay, there is only one normal vector to the plane, although the magnitude of that normal vector can change. There is only one normal vector to any plane, and A is a known point. The A dot n part just there, so the A dot n part is actually two known quantities. So what we can do is we can just write those down as a new constant, and we'll call that constant D, which is a scalar, because the scalar product of A and n is definitely going to be a scalar. Now that leads to the equation of a plane. A very simple looking equation of a plane that r dot n equals some scalar quantity d, where r is the generic point. It doesn't say it in there, so you might want to put that back down. You have got it in your notes previously. So r is a generic point on the plane. We don't know what it is. It could be anything. N is normal to the plane, and d is some scalar quantity. Okay, pause the screen if you don't want to move on. Find the equation of a plane. So let's have a quick look how we could find the equation of a plane given 3 points on the plane in the form r dot n equals d. Okay, so that's what we're going to look at. What's the equation of a plane in that form that contains these 3 points? And a bit like straight lines only need 2 points to define them, lines only need 3. Unless those 3 points are what? Have a think about it. What's the problem with those 3 points when we wouldn't be able to form a plane? Okay, if you guessed parallel, all on a line, then you'll be correct. If you'd actually got all those 3 points on the same line on the plane, you wouldn't be able to work out the equation of the plane. They've got to be 3 points that do not all lie on the same line. So any 3 points that don't all lie on the same line, you can definitely work out the equation of a plane from there. Okay, so see how. So to write the equations of a plane in that form, we need to get the normal vectors to the plane. That's the first thing we need. We need that n value just there. We also need to figure out the d, but we'll come to that second. Let's get the n value first. So to get the normal vectors to the plane, we need to find any 2 vectors that lie on the plane. So I've got 3 points that lie on the plane, but I don't have any vectors yet. Okay, I know how to work out vectors to get to those points, but I need the vectors on the plane. Now at this point, you can choose any vectors you like of the 3 sides of that triangle. So that could be an option, A, B. All right, and you could do it using your normal skills with vectors. So we can see that we're going back down A, so it's minus the A value plus the B value, gets you 214. 214 is a vector that definitely lies on the plane. Now you could do AC or BC, doesn't really matter, so I'll choose AC plus the 520 is going to get me 543. So there's 2 vectors then that definitely lie on our plane. Okay, so they both lie on the plane. Now, because I know 2 lines on that plane, I can now work out the normal vector to the plane. Because if I can find the normal vector to both of those lines, that is definitely going to be the normal vector to the entire plane. For it to be perpendicular to both that one and that one, it means it will be perpendicular to every point on the plane. Right, so I can calculate that using the scalar product, which is just going to be A crossed with B. So I can find the scalar products of both of those. And at this point, hopefully you're skilled enough to be able to do it yourselves. You could use your calculator if you had to. Okay, so I'll do that times that plus that times that. So minus that times that. I would do 4 times 5 minus 2 times 3. And I would do 2 times 4 minus 1 times 5 to get me the answers just there. Now that vector is a normal to the plane. Okay, different magnitudes of that, different multiples of it will also be normals, but that vector just there is definitely the normal to the plane. Right, so what about the d value then? How do I go about working out the d value? Because now I've got x, y, z dotted with minus 13, 14, 3 equals d. Now the r value, the x, y, z, can be any point on the plane. It actually represents every point on the plane. So I could use any point to help me work out the d. Now I've actually got 3 choices then. I could use that one, A, I could use B, or I could use this one here, which is C. Any of those should be able to help me work out D. So I'm going to use, in this case, A. I'm going to dot it with that one, and hopefully that's going to tell me what the D value is. So there we go, 0 times minus 13, minus 2 times 14, minus 3 times 3 equals minus 37. My D value is going to be minus 37. And at this point, you could look at it and say, actually, could I pick the other 2? And if you did pick the other 2, All right, either of those other 2 points, notice they always get exactly the same answer. And that's a nice way to check. Was I right? Well, it's true for that one, it's true for that one, it's true for that one. Yes. And you can leave that exam question knowing you got it right. Okay? So it doesn't matter which one you picked. All right, so once we've got this stage then, we've got our D value. At that point, don't forget to finish it off. Don't forget to actually write what they want, which is in this form. So we end up with r dot blah, 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 blah equals minus 37. And that is it complete then. That is the equation of the plane in that form. Okay, we'll look at other equations. You already know another equation of a plane from what you did before, but that is an alternative way of writing the equation of a plane. Okay, so take a plane and any node point on that plane, same as before. So you might be thinking, isn't this just a recap or a repeat of what I did previously? Not quite. It's looking at an alternative form of another equation of a plane. So there you go, same idea. There's a known point on the plane. So I can put my next thing, take any two non-parallel vectors. Okay, so they're not allowed to pick two that are in the same direction, that are in the same direction as the plane. In other words, they lie on the plane. So I can pick any two vectors. So there's B and there's C. It doesn't matter which ones I pick. A is that one, so I just ignored A. So I've got B and C. So B goes off in this direction, C goes off in that direction. Any two vectors would have done. Right. You can get to any other point now. Doesn't matter what point it is on this plane. You can get to any other point using multiples of these. And it didn't matter which two vectors I picked to start with, this trick always works. If I want to get from A to P, I should be able to use multiples of B and C. So for example, if I want to get to P, I would use some amount of B and some amount of C to definitely get me there. So some amount of B and some amount of C. Okay, let's look at that from a different P. There we go. Pick another P somewhere on there. Can I get there by using just B and C? Yes. Some amount of B to get me to there. Some amount of C, even though I'm going backwards, to get me to the point P. And it works on points on this side as well. So if I want to get to there, I could go back on B, but that's fine, as long as it's in the same direction. So some amount of B and some amount of C. So every single point, I should be able to get to it. And in fact, that's how Cartesian grids work. From the origin, you can get to any point by going a certain amount across and a certain amount up. Now, the Cartesian grid is nice squared paper. It doesn't have to be. If you had just any two lines, so for example, if I just had a grid made up like this, okay, in that direction, almost like wonky squared paper, it would still work. That I could get to any point I like by going a certain amount across and a certain amount up here. Always works. Okay, right. So how does that help me then? Well, that helps me to start to formulate an equation of a plane, another equation of a plane. So to get from A to any general point, all right, I could have a certain amount of B plus a certain amount of C. Just seen some examples of that. A certain amount of B, so I've got a certain amount across in the B direction, and then once I'm happy, I've got a certain amount in the C direction. I can get to any point I like. I also know how to get to A. Now to get to A, from the very starting origin point, I can go from O to A. So to get from O to P, to get from there to there, I would go from O to A, and get to there, plus I would go a certain amount across on my B, plus I would go a certain amount across on my C. Now that is starting to form a general equation of a plane because it refers to any point on the plane. Now, any point on the plane, O to P, is better written as the R vector. R represents any point on the plane, X, Y, Z. So I can rewrite this in a vector equation of a plane. So a vector equation of a plane in your notebooks then, please, is an equation that looks like this. To get to any general point on the plane, I go onto the plane to start with, plus a certain amount of the vector B, which is a direction on the plane, plus a certain amount of C, which is another direction vector that lies on the plane, but it's not parallel to B. B and C must be two non-parallel vectors that lie on the plane. Now, for the keen eyes amongst you, if I got rid of that bit just there, you'll notice it's the equation of a line. The vector equation of a plane and the vector equation of a line are very, very similar. The plane just has this extra vector added on the end. Okay, just for your notes. So A is a vector to a known point on the plane. Okay, a vector to the known point on the plane. So a position vector, as we called it before. The B and the C are direction vectors that are parallel to the plane, but not parallel to each other. Okay, so they lie on the plane or they in the direction of the plane, but they are not parallel with each other. That's an important fact. Lambda and mu are just some scalar quantities, some scalar amounts of B and C. Okay, so pause it there if you haven't got a chance to get your notes down. Okay, so the equation of a plane can be written as r dot n equals d. Could be, where n is a normal vector a, b and c. Right, so I can put that vector in a, b and c. Doesn't matter what vector, what values it is. We just need to figure this out. But as I said, any plane has its own unique normal vector, a, b and c, or some amount of a, b and c. The r vector is a general vector, general point on the plane. So I can call that x, y, z. Okay, because it's just a generic point x, y, z that lies on that plane. Right, so if I find out the scalar product of both of those, then I get x, y, z for my general point, dotted with a, b, c equals d, which is some scalar quantity. And now if I expand that, if I do the scalar product, what I end up with is ax plus by plus cz equals d. Now you've seen this equation of a plane before when you're investigating the geometry between three planes. So we've seen this equation before. But what's quite nice is seeing how it links to the r dot n equals d equation of the plane. Those two are directly linked to each other. That's worth just noting that fact that's popped up there, because it's quite easy to find a normal vector in this form. That's what it's saying. If you've got an equation written in this form, for example, 3x plus 2y minus z equals d, then straight away you can say, well, because I've got 3x plus 2y minus z equals d, then the 3, the 2, and the minus 1, 3, 2, minus 1, is my normal vector. Any work at all. Okay, so a vector equation plane is given by r equals some point on the plane plus some amount of 1, 0, 3, so that's a vector that goes in the same direction as the plane, plus mu lots of 2 minus 1 minus 2, another direction of the plane. Okay, so I've got my Cartesian equation of a plane. I'm going to expand it. I'm going to expand that equation to get three equations in terms of x, y, z, because that's what that is. So what I mean is taking the top line, x equals 1 plus lambda plus 2 mu. Okay, so that's the top line. The second line, y equals 5 plus 0 lambda, so I can ignore that, minus mu. So y equals 5 minus mu. And then the bottom line, z equals 2 plus 3 lambda minus 2 mu. So there we go. Right, so once I've got my three equations, what I'm going to do now is use the x and z equations to cancel out lambda. So I'm going to use that one and that one, just solving the simultaneous equation to cancel out lambda. So maybe taking away 3 lots from that line. So what I end up with, if I multiply that by 3, I can cancel out lambda. You might be thinking, why am I cancelling out mu? So if I cancel out mu there, I wouldn't be able to do anything with this one because it wouldn't have lambda in it. So I'm cancelling out lambda, so I can use that second equation. So 3, bottom line is got plus 3 lambda, so I can definitely use both of those by doing 3x take away this one. So I've got 3 take away 2 is 1. 3 lambda take away 3 lambda goes to 0. 6 mu minus 2 mu, being careful, gets me 8 mu. That's what 3x minus z is. What I'm going to do now is use the middle equation. The middle equation I know is going to be 8y equals 40 minus 8 mu. So because I know that, okay, or I can just rearrange it like I put there, it's fine. Do a substitution method. Then I can use that to cancel out that. So there we go. I'm using the substitution method in this case. Gets the same answer. You would have got your 40, you would have got your minus 8y that way, but you notice that you can write it in that form. So what you've seen there is how to go from a Cartesian equation, okay, into this one just here. But also, that's a vector equation into a Cartesian equation. So you can go from a vector equation to a Cartesian equation. And we've also seen how to get from the r dot n equals d form to the Cartesian equation as well. So you've got the three different forms of the lines, of the planes, and you need to know how to convert between each. So look at the other way then. So how do we write this in the r dot n form? So the vectors 1, 0, 3 and 2, minus 1, 2 both lie on the plane. They're both in the direction of the plane. So that should help me work out the normal to the plane. So there we go. If I do that, I should be able to work out the normal to the plane. So if I do that, I get 3, 8, minus 1. That's a normal to this plane, as long as I'm using the direction vectors. Don't do something silly like using the position vector. That will not help. So that gets me the normal vector. Once I've got the normal vector, I can write it in r dot n equals d. There we go, r dot n equals d. Now to work out d, I need to know a point on the plane. Now a point on the plane is the 1, 5, 2. So I can use that 1, 5, 2. I can substitute that in. That is a point on the plane. That's a general point that I can use for r. I can't use these. Don't forget, these are not points on the plane. These are vectors on the plane. So I can't use those. Whereas 1, 5, 2, written like this, 1, 5, 2, is actually a coordinate on the plane. It is a point that lies on the plane. That's why I'm allowed to use that one, not these one. 1, 0, 3, written as a coordinate, does not necessarily lie on the plane. In fact, it definitely doesn't. Okay, so why does that help me? Well, now, once I've got that bit, I'm just get my laser point back on. There we go. Once I've got to this bit, I can expand it. I can work out what the d value is, and the d value equals 41. So I've noticed that I can convert between a vector form to the r dot n form. So it means I can flick between, with a little bit of work, making using the normal vector, sometimes expanding it, I can start converting between these different forms. There we go, leads to the equation in the r dot n equals d form. And finally, what about the other way around then? I'm starting with the r dot n equals 41, and I want to write it in a different form. R is a generic point that can be written as that. I've already seen how to write this in Cartesian by just expanding it. So I can see how to get it to that form. 3x plus 8y minus z equals 41. But how do I get from these two forms to the vector equation? So 3 points must lie on the plane. So we can figure out any 3 points we like. Okay. So for an example, nice easy one would be 0, 0, minus 41. Another one you could have is 0, 5, minus 1. That would work fine. 40 minus 1 gets you that. Of course, I would recommend trying to use horrible decimals, because you could have 0, 0 and then something horrible here. You know, what would it be? Minus 39.8 and an eighth or something like that. So there's no point in using something like that. So you want to be using something nice. Okay, 5 and an eighth, sorry, it should have been. So it's better to try using numbers that work quite nice. Once you've got that one, figure this one out again. What could be quite nice? Well, I could use 14 lots of that and then take away however many of those I need. Okay, so that's 14, 3 lots of that would have got me 42. Oh, I can take away just 1 from that to get me 41. Right, so once you're happy and you've got 3 nice points on the plane, so there we go, 3 nice points on the plane, then all I need to do to be able to write it in the vector form is to figure out the direction between any two of those. And it doesn't matter which ones I pick, same as I've done before. The one between those two would be 0, 5, 40. One between these two could be 14, 0, 42. And once I've got 2 vectors, it doesn't matter what vectors they were, then I can work out any position vector of that plane by saying, how do I get onto the plane? And then can I have a certain amount of that one plus a certain amount of that one? And it doesn't matter which ones I pick. So you can notice here that actually, isn't there lots and lots of different answers? Yes, there is. Okay, there's an infinite set of different possibilities that you could have picked here, which would have led to different vectors here, and your A value could be a whole host of different vectors that you chose here. So it's highly unlikely you would get the same vector equation as anybody else. Okay, it's not very likely at all, but they would all still be correct. Okay, so we've got these 2 answers that we could potentially use now, and these are both vectors that lie on the plane. But notice that because that lies on the plane 0, 5, 40, you can simplify it into an easier vector that still lies in the same direction. So for example, why bother using 0, 5, 40 when you could use 0, 1, 8? It's like breaking it down to its simplest form. Okay, it's in exactly the same direction, but it's a little bit easier to use. If you didn't do that, it wouldn't actually be incorrect. That is still a correct vector, but it might be easier to break it down to the smallest one because it might make some of the calculations you do later on a little bit easier. Same with this one. Notice that 14 and 42 are common factors there. So why don't you take 14 out and use just 103 as the vector in that line. Right, so that's it. We've got 2 direction vectors. At this stage, you might notice that you and your neighbour now do have the same answer as this, or you might have the same answer as the one in the back of the book. Now you've broken them down to the simplest form. But again, still maybe not, because there are lots of different possible answers out there. So an example of a point on the plane could be any of these vectors. So 0, 5, minus 1. It could have been the 0, 0, minus 41, or you could have used the 14, 0, 1, or you could make up a new one. Doesn't really matter. So any example of a point on the plane would work for A. So therefore now you've managed to write the full vector equation of a plane. That means you can go from the Cartesian to the vector equation, or you could go from the r dot n to that one to the vector equation of the plane. You should be able to flick now definitely between any of the 3 different variations of the equations of a plane. It's just worth noting at this stage though that one way of checking whether your answer is still correct, okay, because you'll notice that that was the answer we got in the previous question, okay, and that's the answer you've got now. Now these 2 lines, or sorry, excuse me, these 2 planes are identical, and one way you could check is that your normal vector, in other words what we found there and there, cross products of those 2, it should be exactly the same as the cross product of these 2. Even though they don't look the same, it should get you exactly the same. So on this one, you can see 1 times 3, take away 8 times 0, whereas on this one, 0 times minus 2 minus 3 times minus 1. So both getting you 3. And that's true for everything. So you could check your scalar product. Do I get the same as that scalar product? Yes. That means I am probably on the right lines. That's one way of checking your answer from the one in the back of the book as well. Is your normal vector the same as the one in the back of the book? Yes, then you're probably correct. The other thing worth noting is that in our example we got 152, and on their calculation, on my calculation to work out this this vector form was 0, 5, minus 1. How can you check whether these 2 are the same? Well, not so easy to check, but the way to do it is to see whether you can think of a lambda and a mu value which gets me the same thing. For example, on this one, if I made lambda equals minus 1 and ignored the mu completely, made that equal to 0, I would notice straight away 1 take away 1 is 0, 5 take away minus 1, lots of 0 is still going to be 5, and 2 minus 1 lot of 3 will get me minus 1. Oh, lo and behold, exactly the same as that point. Okay, and that's what it says there as well. Notice what you get if you get the vector of these two. If you did the vector of these two, when lambda equals 2 and mu equals -1, I'm going to get, in this case, lambda lots of 2 minus 2 is going to be 0. On this one, 0 plus 1 is going to get me +1, and 2 lots of that is going to get me 6, minus 1 times that is going to get me 8, and you notice it's the same value as that one just there. Okay, so it's saying that you could use your lambda and your mu values just on this section of it to see whether you can get some of these values. Okay, there should be a lot of sort of consistencies between them. That means you can change your lambda and mu and get the same answer as either on the back of the book or what some of your colleagues have found. Okay, so what I'd like you to do then, I'm going to give you 3 possible answers here, 3 different equations. These are 3 different questions for you to work out. What I'd like you to do, please, is given that vector equation just there, can you find the Cartesian equation? Can you find the r dot n equals d version? Given that Cartesian equation, could you work out the vector equation in that plane and the r dot n equals d equation in that plane? And then finally the other one. Given that one there, the r dot n equals d plane, could you work out the Cartesian? Could you work out the vector? So pause the screen right there so that you've got plenty of time to work out those missing 6 equations of planes. Okay, so hopefully you started with this one, although it doesn't really make any difference. So if we started with this one, we need to start by working out the normal vector. So it's probably worth going straight to this one. If you wanted to go to that one instead by working out as equations, that's perfectly reasonable as well. You could write it as x equals 3 minus lambda plus 3 mu, y equals 1 plus 5 lambda plus 4 mu, and r equals lambda minus mu. And then from there, you could use those equations to work out the Cartesian equation. The other option is to go to this one, work out the normal vector between those two, and then use 3, 1, 0 to work out the d, and then it's very quick and easy to get from there to the Cartesian. It's totally up to you. I don't mind what you did, as long as you got this answer just here, and from this answer you can see that 9 minus 2, 19 is your normal vector, 25 is your d, so therefore you can easily write this one in that form. Once you've got either of those, they're very easy to flip between. That's the tougher one, to either get it or get from it. What about this? Well, straight away, because I've got that Cartesian, I could fill this one in straight away. I know it's going to be r dot 3 minus 18 plus 4 equals 16. But this one's a little bit tougher. So what would I do for that? Well, you want to either, from here, you want to be doing what we did before, thinking of 3 points that lie on that plane. Okay, so 0, 0, 4 could be an obvious one. You might have other ideas to go with these two, maybe minus 18 there, doubled up plus take away some of those. It's up to you, whichever 3 points you want. Once you've got your 3 points, you want to get 2 direction vectors and use any of those 3 points as your first one. Okay, to work out the equation of that plane. This vector equation, you might have some very different answers. So if you didn't get the same answers as mine, it does not mean yours is incorrect. Just check, is your normal vector the same as 3 minus 18, 4? Did you get 3 minus 18, 4 from your normal vector when you found both of those cross product? Okay, or whatever yours ones were. I've used 0 minus 2 minus 5. So 2 lots of that, take away 5 lots of that. Should work fine. 2 lots, that's going to be 36, take away 20. That would get you 16. Again, your answer here could be anything that works in that equation. Okay, so just check it. Does yours work in the equation? So your big tick there, you are correct. This one's easy. R 3 minus 18, 4 equals 16. And then finally this one. My advice first is to fill out this bracket just here. This is a Cartesian equation. And from there, work out any 3 points and do the same bit of maths as you did a minute ago. So did you get this one and did you get that one? So again, If you didn't want to change it to plus 21, that's fine. You could have minus 21 that side. I just want to show you that sometimes they might neaten it up by not having the negative on that side. That's perfectly reasonable to write it as either way round. This bit here, just get 3 points, sorry, and then find out your direction vectors and use one of those points. Again, just confirming that your vectors here get you 4, 6, minus 5. They should do, or some multiple of it. Did your initial value just here, if you put it into that R, dotted with that N, did it get you minus 21? If it didn't, then again, you want to just be checking your answer. Okay, but very well done if you managed to get those. Once you've sorted that, what I'd like you to do is just on exercise 5B on page 91, lots of good practice at working out and converting between different equations of planes. Okay, have fun.